Okay, so now we have a presentation by John Baldwin and Jessica Clarke, and hopefully we'll be able to see that.
Which one?
As the
This
right
one,
button, yeah.
not the stop.
Not the stop, no. And I will introduce you. So Jessica Clarke from University of Cambridge. She has been shaping CHERI linkers since the early days. She wrote the first prototype CHERI linker and continues to work on CHERI LLVM and CHERI BSD. She also brings standard leadership as vice chair of the RISC-V CHERI task group. And John Baldwin has watched CHERI toolchains evolve for over a decade. A FreeBSD developer for more than 25 years, he has contributed across CheriABI, GDB, LLVM, and Morello. His perspective spans CHERI-MIPS to CHERI-RISC-V and explains how we arrived at today's linker models. So, the floor is yours.
So, theory that should work. Yes, so good afternoon. We have an extra 10 minutes, I think, is the takeaway before lunch. So we'll see if we can get away a bit early rather than eating into that. I will warn, though, there are quite a lot of slides of this talk. We have the longest talk, I think, of the conference, and I'm taking full advantage of that. So we may gloss over some of the details here, but the slides will be available afterwards. So please, if you're interested in this, do feel free to go look at them after. And of course, any questions, feel free to chat to us over lunch. So I'm giving a bit of a retrospective here of CHERI linkage. And I think when we go through this, it's important to look at the history of sort of how things came to be, why they came to be, and why we've got what we have today, and where we think we want to take that in the future. So what is the basic problem of linking? So in your source code, right, you write a piece of code, you give things human readable names. So you have your printf, say, for example, here. And that's what we like to think of. We like to think of what we call symbol names. But in reality, the machine code isn't referring to things by names. It's referring to them by addresses, or in our case with CHERI, really by capabilities, right? These are pointers that are flowing all around, all over the place for that printf. So the problem for linkage is really how do we map from this source code abstraction down into the actual pointers that we see when we run at runtime. CHERI introduces some new unique challenges here. So firstly, the capabilities, we have this tag bit on them. So we cannot just put them in a file and load that file up into memory. We have to derive valid capabilities in order to get a tag on the actual capabilities we have at runtime. So today, you see that anyway with position-independent binaries. You randomize the address at which they're loaded, so you still need some dynamism there. But we also see position-dependent binaries still, where the addresses would traditionally be hard-coded, but now we need extra initialization for CHERI. And we have extra metadata as well associated with some of those things, which we'll see a bit later where that can cause some issues. And yes, so CHERI capabilities, they're not just an address, right? So the traditional linkage model we've inherited is tied to the idea of an address. And so all those data structures in there, for example, there's this thing called an addend in a relocation, which is really holding either an offset or an address depending on the circumstances. And a capability just does not fit in there. So that can cause some issues as well that we'll see. So some history then, and you'll see at the top right, I've tried to annotate things with an approximation of how long into the CHERI project everything was. So in the beginning, right, you start off, you're doing new experimental hardware, you have no toolchain whatsoever. And so about a year in, we see the first version of an assembler, but interestingly, not LLVM, right? So everyone presumably here using software is familiar with CHERI LLVM, but in the old days, we were back using binutils as our assembler. So then you continue on with your assembler and you cobble together some programs, but eventually you decide that you want something a bit more advanced. So about 3.5 years in, you then see the appearance of CHERI LLVM. And interestingly, actually, the first commit to add CHERI support to LLVM wasn't just the assembler, but also the beginnings of some rudimentary code generation. But we're not yet quite at the linkage stage. We're just about emitting instructions. So if you have a compiler and you've got some increasingly mature code generation that can emit things to do with capabilities, where do you get these capabilities from that you're using in your instructions? And in particular, if you don't have a linker, how do you get the compiler to do something that approximates it? So there are sort of two cases to consider here. The first is that you're running some code and your code has asked for a capability, so you've decided to mess with a global variable. In that case, you're already running code, so you can insert whatever code you like from the compiler to dynamically create one. So in Cherry, we have this thing called DDC, although back then it was called C0, and that can be used as some sort of global capability that covers everything, and you can dynamically insert code to derive a capability for any global you like based on that. But that's, and yeah, so here's the code. To do that right, you literally just load as an IC. Is there a laser pointer on this? Maybe. There is a button. Not sure. So yeah, so you can see there in the middle, there's this MVT double code on I64. That's basically saying we're loading a 64-bit integer, and then on the final line there, we're doing this int to pointer operation, which is really just a dynamic conversion from an integer to a capability. So nothing really about linkage yet. We're still in the code generation world. What about global variables? So if we have some global variable like this, right, we've said that P is a global that points to X. We're not running code to do that. That's something that exists in our data. And so something somewhere needs to make sure that that's initialized. So for non-Cherry, you can either hardcode the address if it's a position-dependent binary, or there's some kind of runtime loader that's going to come along and fill in the right address when you run your program. But we don't have a linker, and we don't really have a runtime loader at this point, so where's this capability going to come from? So back then, we decided that the thing to do was emit this magic new cap reloc section. So the compiler emits this, and it's a big table that says all the capabilities that you have and what they need to be initialized by. And so this is about 5 years in, right? 5 years to the day without any kind of linker support. And so then the OS can iterate over this section, not in a runtime linker, but a little bit of startup code, and it can do whatever initialization is requested. So let's focus on this second bullet point exist. Does anyone recognize this thing? Hand over there, hand up back there. So let's look at a binary from about a month ago, and it's still there. Right? So this thing was made 5 years ago before we had a Cherry linker, and yet we're still using it today in some form. So as I said, it predates having a Cherry linker, and in fact, the format was designed to not need one, right? It was designed to reuse existing things that were there that could be sort of abused to provide what we needed. It was also conceived for CHERI-MIPS, and it predated 128-bit compressed capabilities. So back then, everything was 256-bit capabilities, and that sort of reflected in some of the lack of compression in the data types as well. So on the left here is what was the first version committed to Cherry BSD, and on the right is what you see today in CHERI LLVM in the header that it provides. And really the takeaway here is that almost nothing has changed. The types have gone from being hard-coded 64-bit to being parameterized based on whether you're 32 or 64-bit. And I guess the start and stop things have gone from being non-arrays to being arrays, but everything really is just the same here. So what are these different fields in here? So these first two, they are just 64-bit addresses. So the capability location is saying, where do you want to store a capability? And the object is saying, what is the base of that capability that you want? Typically, for example, in our previous example, the first one will be P, and the second one will be X. The third one there is what offset do you want the capability to have? So in our case, it was 0, but if you said X plus 1, then you would have an offset of 1 or perhaps 4, given that it was a 4-byte integer. And that's a compile time constant. This permissions thing at the bottom, when it was first committed, was aspirational, but existed. And the size of not annotated, we'll get onto that on the next slide. So what sets this size? Where does it come from, right? This is one of the core things of Cherry, is having these bounds. So back then, there's no linker, so you need something else. And this was this new cap size fix tools. And what it would do is it would go iterate over all of these cap relocs. It would say, well, what address have you asked for? Okay, then let me look at all the symbols you have. What symbol is at that address? And then go find the size associated with that symbol and copy it into the corresponding entry. A little bit backwards, but that's about the best you could do at the time. Okay, so then that gets us our globals. Let's go back to our deriving dynamically case. What can we do that's a bit better? In particular, where can we get our sizes? So if it's a static variable, then actually the size is known at compile time, right? We can just ask size of and put that into the generated code. But what if we don't know actually at compile time where x is, which x we're using? Maybe we have a type, but we don't trust it. Maybe it's an array of unknown size. We don't know that information until link time. So as a solution here, we say that if a compilation unit decides to define an x of some type t, then the compiler is going to automatically emit a new magic symbol called .size.x, which is a constant that contains the size of x. And so then in your compiler, if you don't have a known value for the size of x, you can go and read this global constant and go use that as the input to cset bounds. So then to put that all together, so if we have a function here whose job is simply to return the address, or in our case, capability to x, it's a 5-stage process. We have to go and get the address of x from this thing called the got via our default data capability, because we don't yet have any capabilities lying around. We have to go get the address of this new magic.size.x symbol to find out how big x actually is. We then actually have to go and read what's in that variable to find the actual size, again via DDC, because we've not yet got a capability to it. Then we can take our address of x, we can use our DDC still to convert it, and then finally we can do our cset bounds with the size that came out of step 3. So that's 5 instructions, 3 of which are loads. There's some dependency chains in there between the instructions. And also on top of this, this is code that's happening every single time you run f, right? So that code exists in the binary, so it's taking up disk space, and it's taking up dynamic cycles as well every time you call the function, when really this is a thing that's not changing once the program starts. And on top of that, we want to have memory safety, but for all this to work, we have to have this DDC that covers the entire address space, because you could ask for any global that you like. So this all seems rather sad. And then there are even more awkward questions. So this was all talking about static linking, where you embed all the libraries you need into the final executable that you build. But we don't build systems like that. We build them with dynamic linking, so that you can update individual libraries, you can share them between processes, and not have to take up a whole load of disk space and memory. So it can kind of work, right? If x and .size.x always go together, and all your rules that you have for when one is visible replicated to the other, and all the versioning that you have, you can kind of make that work. But for cat relocs, it's kind of a bit dodgy. So this capability location thing and the object, well, those now need to have relocations associated with them to say, well, I don't know which x it is, so look it up at runtime. That's no longer a cap size fixed time constant. So there's this weird sort of 2-step relocation process where you use the normal ELF relocations to change the addresses of everything as if it were non-Cheri, and then you go process the special Cheri relocations. So you have this sort of weird relocate the relocations themselves process. The offset, at least, is always a compile time constant, but the permissions and the size, how are you going to encode that? There's no existing relocation to go and get the permissions for something. There's no existing relocation to go get the size of something. So complications exist here. So we want to do something better. We want a proper Cheri linker. So the first step is that we don't actually change anything, but we just move cap size fix away from being its own tool, and we put it inside the existing LLVM linker LLD itself. So the compiler emits everything as it did before. The runtime sees exactly the same thing that it had before, but we've now moved and abstracted over what the linker is actually doing. And now we have stuff in the linker. This cat relocs format is really unhelpful, right? So if you remember this cap size fix tool, it was having to go and look at the addresses that we had in this cap relocs table, and then go map those back into symbols based on their addresses. Well, really, the linker just wants to know the symbol, so why can't we just tell it the symbol now that we have a proper linker? So that is indeed the first step we do. We ditch cap relocs from the compiler, and we just have it emit normal sets of ELF relocations that give symbols. And then the linker, because we want to maintain the runtime, just emits the same cap relocs that the compiler would have emitted for that. So now we have a better interchange format between compiler and linker. And then the next step, right, so we wanted to avoid this 5-step dynamic derivation process. So we have this thing called the got that stores a whole bunch of addresses traditionally. Well, really what we want there is we want an equivalent that's got capabilities in it, right? And so if we build a table of capabilities, we can use our cap relocs mechanism to go and initialize this table ahead of time. And so instead of having to do a 5-step process, we can instead just say that to get a pointer to x, we find the entry for x in our table, and then we just load from it. And so now we're 7.5 years in, and finally we're having something that starts to look like what we see as modern Cherry linkage. And then we have bounds. So now that we have a linker, we can go and look up the sizes and types of the symbols that we're looking at. So the linker sees all of the libraries that you're linking against, even when you're doing dynamic linking. So it can go and put in appropriate sizes for things. But this CAP-RELOCs format, we still have this dynamic linking problem where really it's not designed for dynamic relocations. It's designed for that very static linking case where you can compute everything and hard code it into this big table. And on top of this, right, in this dynamic linking world, that object, which is saying what address do I want my capability to have, that's having to use a normal ELF dynamic relocation to go and look up what that address should be at runtime. And that normal relocation has with it a reference to the exact symbol that it wants the address for. Well, that's just the symbol that we want to go find a capability for, so why are we bothering to go find the address for the symbol, put it into a table to then only go and construct a capability? Why don't we just short circuit this and just go find an actual capability to the thing from the start? And so that's what we do, right? So we change the system now where we have a single ELF relocation, a new Cherry capability one, that gets as it a symbol that it wants to get a capability for, and just writes that in place. So for all these cases, suddenly we've got rid of this CAP-RELOCs format entirely, and we just have a single ELF relocation exactly like you would have on non-Cherry, except it gives you a capability, not an address. At the same time, sort of to try and patch things over, because trying to introduce a new type of relocation like that was a bit more invasive, some attempts were made to also make CAP-RELOCs a little bit better. So add some new relocations that are still integer relocations, but go query properties of the capability you would like and go fill in the CAP-RELOCs field. This was quite short-lived, but it did exist in parallel at the time. And so this is the point of time in which we published our CheriABI paper. So back in 2019 at ASPLOS, this was what we were using. And then shortly after that, we had a couple of extra quick additions. So the first one here, right, if you have that your global variable x is a constant, at the time, we were only differentiating between functions and data. And so if you wanted to make x be constant and enforce that, you still relied on the MMU to do so. But we have capability permissions. We can clear write permission on a capability. So really what we'd like to be able to do is not rely on the MMU, whether because you have a system where you don't have an MMU, or just various complications where actually you kind of can't go and change the MMU to be read-only. And so we extended this CAP-RELOCs format to include a constant flag as well. So we have this new relocation that's being used for what we call symbolic relocations, for all these ones where we have to go and look up dynamically at runtime what capability we would like. CAP-RELOC still lives on, though, for the cases where you don't have a symbol, because you lose all that information if it's something that you don't have to go look up dynamically. So in these cases, these are for all the things where you know that the variable that you're looking at is within the same library as the reference to it. And so in those cases, the size and permissions are now constants, so we don't need any kind of relocation for them. The location and object, those still need to be absolute addresses, but now they're always going to be within the current library. So if it's a position-dependent executable, those will be known link time constants. If it's something that's position-independent, such as a shared library, then we need to go and add on the offset at which we loaded our library. But that's going to be the same for every single entry in the table. Either we do it for all of them with the same value, or we do it for none of them. And so having to omit a whole bunch of relocations to fix up these CAP-RELOCs entries to have the right absolute addresses, that's now quite a high inefficiency that we have, and we no longer need it. So instead, what we can do is we can say that we can implicitly add on what this offset is. Right? We scan through the table. We know that these all refer to the current library, and therefore we can just implicitly add on the address that we loaded the library at. And so then along came a little thing called Morello, 9 years in. And so 10 years in, we saw the open sourcing of Morello LLVM. Now, at this point, we're sort of not getting any public history to chronicle because Morello support landed as one giant commit to hide all the internal development work rather than try and sanitize all the history. So we can't really do some of the same archaeology here. So what did Morello bring that CHERI-MIPS didn't have? Well, first of all, for our capability table on MIPS, we had kept the existing GOT as storing addresses as a sort of transitional process, and therefore we'd had to have a new section to store these capabilities that we called the cap table, and that all existed as parallel code inside the linker. Morello, coming along a bit later, didn't need to maintain that same amount of compatibility, so it just took the existing GOT code and repurposed it to also support capabilities. It also added a thing called lazy function symbol resolution. So this is something that exists on most traditional architectures that lets you say that if you're not calling a function, you don't have to go look it up until you first call it. MIPS and thus CHERI-MIPS kind of didn't do this properly, so we never really had to consider it. But baseline AR64 had this as a feature, and so the Morello design made sure that this worked as well. And it also invented this new ELF relative relocation format that was to replace cap relocks. But it still kept cap relocks around as well. We have finally just about transitioned CheriBSD off cap relocks, but as of a couple of years ago, we were still using it there. Also, it introduced this notion of narrowing the bounds of the program counter for function symbols. So on CHERI-MIPS, we had an approach to do so in the runtime linker, but Morello was really trying to do it more inside the static linker itself. And then finally, there's this thing called start-stop symbols, where if you want to put a bunch of arbitrary data into a section, you can get markers to the start and end of the section so that you can iterate over it. For Morello, they added the support to have padding in there so that you can ensure that your capability is representable and doesn't give you access to other sections you shouldn't have. So this relative relocation format to replace cap relocks. So what is this? So they introduced this new thing called a fragment format. It packs three things. It packs in the base, which is a 64-bit address. It packs in the size, which they constrain to be 56 bits. And finally, in the top 8 bits, it stores a little bit of information about the permissions. So that will tell us read-only, read-write, or read-execute. And also, yeah, so the final thing, the offset, that gets stored in the add-end field that already exists inside ELF relocations. And so this new format gets used for several things. It gets used primarily for this thing called Morello relative. So if you're ever familiar with what a relative relocation is on non-CHERI architectures, it's just the CHERI equivalent for that. And there's also an I-relative one if you know what I-funcs are. And if you don't worry. Most people don't and shouldn't. And so, yeah, so these are similar to the non-CHERI counterparts. And then also for this lazy binding support that they introduced, this is the same format that gets used for the relocations there as well. Okay, so PCC bounds. So PCC, our program counter capability, we use that to access the current GOT for the library. We use it to jump to functions within the library. We use it to jump to PLT entries for calls outside the library. We use it to read various constants from constant pools. So for example, if you have a floating point constant, it's often cheaper to just load it from memory rather than go and try and synthesize it in a bunch of instructions. And the bounds that our capability has to include all of these for our code to work. And so the static linker here can determine which of the sections it's emitting can be accessed via PCC. And then it can say for the first one, it needs to align it to ensure the capability is representable. And for the last one, it can pad it to the representability boundary. And then what it can do is it can bake this into the actual relative relocations that it's emitting. So it can set the base to be the address of that first section. It can set the length to be the difference between the end of the last and the start of the first, including the padding. And the offset can be where that function is relative to that start of the first output section. One thing here, though, that's missing is that this is done for all the relative relocations, but if you have a dynamic relocation that's got a symbol associated with it, you still need to go query what the bounds of PCC should be. And so at this point in time, there was nothing being emitted by the static linker to tell the runtime what it had computed for these various things. And so the runtime loader has to try and infer what would be appropriate and doesn't quite have enough information to be able to get it right. So you end up with subtly different bounds sometimes. And so then RISC-V starts to enter the picture. from this point, John will get to talk about sort of more the present and where we're going.
All right, how's my volume? Thanks, Jess. The badge little dingle keeps interfering. All right, so what are we doing more recently? What are things we've been doing on LVM, both Jess and I and a few other folks? The first kind of work we've done is we've had this more recent project of working on refining compartmentalization, but we had to do some kind of prep work, so lay the groundwork for doing that, both to help library-based compartmentalization, but also when we looked at many of the things that ARM had done with Morello LLVM that Jess just went over, several of those ideas seemed like worthy things that we wanted to bring across to CHERI LLVM, at least in some fashion. So some of the things we pulled across, we really liked the idea of standardizing how the GOT worked and treating the GOT table, the cap table as a real GOT. By leveraging, making that a real GOT inside of LLD, it means that it made it much easier to deal with the fact that you actually have multiple GOTs. So you have a separate GOT for your PLT, which makes it then a lot easier to do lazy symbol resolution also for CHERI-RISC-V, not just for Morello. One of the things that we needed for library compartmentalization is in library compartmentalization, when you're calling a function that crosses into a different compartment, we need to be able to interpose on that call to install a trampoline that does extra work to try to manage transitioning your state between compartments. But not all pointers to a chunk of code that your C and C++ runtime need to actually do a function call that transitions that boundary. In particular, some of the pointers that point to code that are used for C++ exception handling, for landing pads, for example, they actually need to point to the real thing, and they need to not be interposed. So we had to add a new class of code relocation, or a kind of function-related relocation, so we could differentiate between when are you calling a function, and it's okay to interpose on it, and when are you directly accessing the code in some fashion, such as during unwinding, and you need to not be interposed. So we had to add a new relocation for that. Another thing that Morello had was indirect function support, and we didn't have that in any of our CHERI platforms before. In fact, well, at least in CHERI-BSD, we didn't have it even for RISC-V yet, based on RISC-V. And Jess worked on that so that we were able to extend cap relics to support a notion of ifuncs via kind of new pseudo permission flag so that we could handle ifuncs in the cap relics format. Another thing that Jess talked about at CHERI Tech a few months ago, or 6 months ago, I guess. She gave a whole talk of this. We won't dive into it more here. But we reworked the ABI of how TLS works. Previously, when thread local storage worked with CHERI, the pointers that we created, kind of, you got the bounds of your whole block for your, whatever your shared library is. And they relied on either code gen or other things to kind of narrow the bounds for you. And Jess has introduced changes that provide much better safety, that we make sure that we're handing out bounded pointers all the time. And also it makes it we're able to filter the sets of available variables you can see for compartments. And then we also did some of the changes related to PCC bounds. These are adapted from Morello, but with a few changes that we did on ourselves. So let me dive a little bit more into that. So these are some things that we made different to how Morello was handling PCC bounds and its implementation to what we ended up doing in CHERI LLVM and then pushing back into Morello LLVM. So the way that Morello LLVM, as Jess mentioned, decided which sections should be covered by PCC is it had a static notions kind of knowing, for example, all text sections always need to be covered by the PCC and all your GOTs, and probably all row data, the end. But Morello had an interesting code gen choice in pure cap mode where sometimes it will decide to create a kind of pseudo GOT or a pseudo cap table that lives over in the data.railrow section. I think it gets used sometimes for pointers to non-preemptible symbols. And Morello LLD wasn't taking this into account. And so if you actually trusted the bounds that were in cap relics for Morello LLVM, what you would find is that many of your programs, at least in our experience in CHERI-BSD, they didn't work. Like our kernel couldn't boot because we ran an ifunc resolver for memset, and the pointer it tried to return from memset was out of bounds because it was over in this data railroad section. So we couldn't even make it to like printf in the kernel booting. So one of the things we refined is that instead of just having a static list, we would actually look at all the elf relocations that a given file was, all the input files we're using when trying to build an output file, and see which of those relocations were PC relative, And if they were a PC relative relocation, what section were they targeting? And make sure all the sections that were being targeted by a PC relative relocation were pulled in. And that would find cases that if you did have a reference to data.relrow, we would find it and know to pull that into the PCC bounds, but only if you actually used it. And the same with row data. So instead of always pulling in row data, we only pulled in row data if you actually put a constant pull there, not just every time you had any type of constant. Another change that we made is that the way that Morello LLVM was achieving the padding so that the PCC would be representable is they just added zeros to whatever the last section was, which was usually the GOT, so it didn't hurt. Your GOT just looked bigger. Adding arbitrary zeros is also not ideal when things depending on the size being correct of your section. So we instead added an explicit little helper section, like a pad.cherry.pcc, that's whatever the padding is, and just make sure that, just some gross code to make sure it's the last thing in your PCC bounds and to manually resort the section after the normal sorting. And then a change we made after that is that once we had this notion that we could figure out which of your output sections actually need to be covered by the PCC, we had noticed that in the default layout that LLD uses, it would kind of intermix some sections that needed to be like text and sections that didn't need to be like that data and then got after that. So we took advantage of, now that we have this knowledge, we've tagged all the sections while we're doing sorting to know which ones need the PCC, that we could group those all together to make our PCC bounds as narrow as possible and move things like that data out from under the PCC bounds. And then the last change that we made, was to the last point on when Jess was talking about this in Morello VM, is we added a new ELF header, a new ELF program header called PT Cherry PCC. And it's not like an actionable header the way PT load might be. It's an information header the way like Railroad works, where we describe an address range saying what the PCC bounds would be. And the runtime or your dynamic linker can then use this information that anytime it's resolving a function symbol that lives inside your library, it can look at this new ELF header to figure out what the PCC bound should be. And it doesn't have to reproduce the logic that the static linker is trying to use. Instead, the static linker has communicated whatever decision it made, and the runtime loader doesn't have to be fancy. You could just use this header out of the gate. It's got the right bounds in the end. So let's talk about the next thing that we are more actively working on, which is a refinement to our library compartmentalization model. So baseline PureCap CheriABI gives you some isolation between shared libraries. Their PCC bounds are disjoint, right? So you can't directly get with your PCC from one library to the other. And our ongoing research into library-based compartmentalization is strengthening that isolation. We're patching up a few more leaky places like stacks and so forth. But oftentimes, we may find that we would like to decompose libraries and executables into smaller boxes than what we happen to be doing today as our software engineering sized boxes. So one way you could do that, leveraging library-based compartmentalization, is you could just split your existing shared libraries into smaller shared libraries. But that's a giant pain in the butt. Because now you have to go refactor your build system to build like multiple libraries instead of one library. And what if you want to actually split up source code? You've got to like split up your C files or put really horrible if-defs so that it only compiles half the file when you compile it one time, then the next. That's really terrible. And there are various other problems, like you have symbol versioning that's a version map file. Now you've got to split that up. And every time you want to change what the layout is, you have to redo all this whole changing the things around. That's a giant pain in the butt. So we would like to do a different approach where we can have this flexibility to have smaller boxes but not break your software development model. So we're going to try, and my animations are slightly off. We're going to try something. I'll walk through an example of what this might look like. So today, if you have a libping, this is the way libping normally works. You've got all your code together in one spot. Yeah, I don't have a button. All your code together in one spot, no matter what it does. One big giant data, and a GOT that has access to all the symbols that any part of your code wants to get to. And the GOT contains references to things that are outside of the shared library, so other functions you need to call. And what we do when we split, in this case, we're going to split the library. We're going to create what is in memory, basically, from the memory's viewpoint, multiple libraries. So each compartment, each sublibrary has its own GOT, its own data that are the variables that that part of the library needs, and its own code. And each GOT has references to the things that it needs. And you can see we have an example of one arrow going from the GOT of one part of the library to a function in another part of the library. So in memory, it looks like separate libraries. And you have all the same linkage and GOT indirection as if you had actually had separate libraries on disk that you mapped distinctly into the address space. But on disk, it's a single file. And at build time, it's a single file. So you don't have to change your build system. Instead, the way this works is that we have a kind of JSON file you can write where you can dictate which symbols or which object files go into which compartment. So you can decide, using this policy file, how is the linker going to decide which parts go into the IO compartment or the default compartment in this case. And it turns out, without any changes to source code, just a single argument you add to LD flags when you're building your thing. And you can try different things out by just changing this one JSON file. So this is an example we did with JSON, where we did kind of a hand-engineered compartmentalization strategy where we split it up into two compartments. One of our research partners did some work with their own tooling and gave us a different policy file that created, I think, like 10 compartments. And all it was basically substituting their JSON file in place of the one we had done and rebuilding the source code, or relinking everything, and you get a different output library. And the user ABI of that library, how it interacts with other binaries in the system, doesn't change. So you could, like any other library upgrade, you could just replace the library and it kept running. So how does this, like what are changes we do to make this work? So we had to interpose a bit on intercompartment access to make it look like multiple libraries. So when you're now calling inside of your library to a different compartment, you can't just do a simple relative branch like you would do without compartments. You have to treat it like it's another library, so you have to actually go through the GOT. So in order to implement that, we reused something that LD already has in place to handle non-preemptible indirect functions. If you take a pointer to that, it's got to store that somewhere and resolve that. So it creates these kind of special GOT entries for those that use relative relocations, and we really reuse that same function to handle cross-compartment calls. Another thing we add in our policy is the ability to place restrictions on which symbols you want to import into a given compartment. So you have an ability to specify an optional ACL, which is a white list of all the symbols or compartments perhaps that you want to import symbols from, and what permissions you're allowed to use for those given symbols or compartments. And if you break the rules, you get a link time error to tell you that you didn't satisfy what your policy was doing. And the ACL can also constrain permission. So there's the ability for you to say that I want, even though it's a variable that happens to be in a writable segment, maybe a writable segment of the shared library, I know I only need read-only access to that variable, and I can end up with a read-only pointer in my GOT, even though it's a writable variable. The other thing we did for this is we added yet more extensions to ELF. We mentioned PT CHERI PCC before. We've added some more things so that the dynamic linker or your kernel linker can know about what's going on here with different compartments, how to enumerate them, know which address ranges belong to them. So you've added another string table that has, for example, the names of compartments inside your binary and a way that you can find it by parsing your dynamic section. And we've added another ELF program header, which is also an informational header the way PT CHERI PCC and Railroad are, which describes a single address range and tells you where in memory a given set of addresses belong to a compartment, and then we abuse the physical address field to be the offset to the string table that you can use to find the name of the compartment. And it's intentionally by design, it's not required that you only have one of these. You're allowed to have multiple of these that map to the same compartments. Your compartments can be disjoint. It's just a matter of, this gives you a way in the runtime loader that you can map an arbitrary address back to a compartment when you're trying to do, if, for example, you have some kind of rules evaluation about symbol resolution in your runtime loader. The things that we would like to do in the future, and this is not an exhaustive list. As Jess mentioned, CAP-RELX is it's a funny, well, we have a love-hate relationship. Maybe that's a way of describing CAP-RELX. And ultimately, the thing that I've heard many times from Jess and from Alex and from others is what we would really like to do is do something that's a bit more like a normal relative relocation. One way to think about normal relative relocations on architectures today is you kind of have a template that you add, and you just add the base address and slide it forward. And we would like to have something that is kind of like that, but capability shaped, so that the thing that's in your file not quite the fragment format from Morello, but more like the actual template capability that you can just relocate forward. And the linker is already written, the permissions exactly the way the architecture specifies them. So you really get a capability that's just not relocated yet. And then basically you relocate it forward and use cbuildcap to actually tag it. And Jess even has a proposal for a crelocate instruction you can find in V9, the V9 ISA that kind of optimizes the set of instructions you need here to make this as quick as possible. And we would like to merge, eventually we think Morello support into CHERI LLVM, just to make it easier to have fewer versions of LLVM around. We also, of course, would like to have all of our LLVMs more in sync, but we think this one will help us. And particularly as we've been working on our compartmentalization work, we keep all these parallel branches that we have to keep parallel across two repositories, just quite a bit of work. So I think that's our time of history. Where are we at on time? We have 30 seconds. Yeah.
Oh, questions here.
Thank you for the talk. If I understood right, then for sub-library compartmentalization, you are actually creating a PLT in GOT per compartment. Is that right?
Yes.
So given that the number of the GOT and the PLT is determined at build time, does it mean that you have to have a fixed number of compartments?
Well, so we have a limitation currently on the number of compartments in a single shared library, which is 128 because of the way LLD currently sorts sections. We used a functionality uses for something called partitions, and it's like a 7-bit field in this integer that's used for ranking. But that's the only limitation we currently have is more of this kind of internal detail of LLD, which if you needed more than 128, you could refactor how it sorts to fix this. But there's nothing inherent in the ELF design. You're allowed to have several GOTs and PLTs. In fact, what happens on the dynamic linker side is today, when you have a GOT PLT, you emit a couple of tags in your .dynamic that tell the runtime linker where your jump table, your PLT is, where the relocation table for your PLT is, where the base of your GOT address is, and how many entries it has in effect, how long your relocation table is. And we just emit multiple tuples of those, one for each PLT. And then the runtime loader can know, well, effectively it gets a bunch of tuples of those things and can enumerate all the PLTs and set up all the PLTs to work. It doesn't actually have to know their compartments. It's kind of orthogonal the way we implemented it.
Okay, thank you.
Success on this occasion. I was going to make two comments. The first is, I mean, for many audiences, the arcane knowledge represented by your description of linkage would be too much. But in this audience, you had people taking photos of changes to PLT. I'd sort of say that is a truly remarkable accomplishment. I don't want to characterize in what way it's remarkable, but it is remarkable. Second comment I was going to make is, one of the challenges in running this very long-running project is the degree to which you have to build scaffolding on top of scaffolding and only partially understanding what you're doing when you're doing it. I think we probably would not have taken quite such a circuitous route to the end goal if we'd known exactly where we were going. But actually, a lot of the steps that we're taking were really the next natural step, right? Because you need to keep things running, you need to get the next thing working, and so on. So I think it's a really interesting thing in the history, but maybe there's one moral, which is worth sharing, which is that co-design between hardware and software, etc., takes years and years and years and years. It's a very long, drawn-out process. You get a ton of experience, and sometimes you get something that is a really good outcome, or close, and then you work on it. It maybe is a cautionary note, which is, each time we try to change the CHERI model, we have to go through this kind of process and evaluate it. It's very hard to know what takes you to a next step, which is the right step. And when we're looking at future design choices, and we have all these nice slides about coming research, and oh, so exciting, and all these ways to do temporal safety, it's really important to recognize that we'll be looking back on that work in some number of years in the future. Many of those ideas won't work out, right? Or they'll be the wrong step, or they'll get us to the right step. We need to be very cautious about adding new things to CHERI to make sure that the things that we're getting into production use and into standards and so on are the right things. And I'm sure that if we ask the CHERI folk, they'd say all the steps they took in various aspects of the co-design around temporal safety there, multiple tries, got it right the 5th time or something. So it seems cautionary. and I don't mean to be too negative, but I think it's very important to look at the research in the coming sections that everybody carefully manage expectations about what will be achieved as you change the model. There's lots of great stuff still to do, but a great deal of caution is required. Anyway, thank you for the talk. I actually have no questions. That was just comments. I didn't even put a question mark at the end of any of those comments.
I would have found a question more scary.
Throwing in a thread.
Because I just said what he did.
Yeah, thanks for that reminder of the history. Like, I'd forgotten a lot of it, or maybe suppressed it.
Yes, it was interesting looking back and seeing the odd order some things happened in that didn't match my memory.
Yeah. I was wondering, like, with the sub-library compartmentalization, have you tried, like, basically reviving the, like, per file, per function stuff? Obviously, there's limitations with numbers of compartments.
So I looked at it, and I should say this. When we were first starting discussions at the start of the CPM program and talking with some of the other performers and describing how we could do smaller boxes in Cherry, smaller compartments, it was actually your work that I was aware that there was the idea that we could have per function GOTS if we wanted them. Like, that was one way that you could get there. I think I took a different route to try to do it all on the linker side instead of having to do code gen, and to allow us to do more arbitrary breakups and not just file and just function. But certainly I was aware of what you did, and it was like in the back of my mind. Like, there was a distinct time I told one of the other performers, oh yeah, we could do per function GOTS. And I was directly going back to, oh yeah, because Alex did per function GOTS. So you were definitely the inspiration for what's there now.
Yeah, I hope you didn't reuse any of that code, because it was...
Well, let's just say that for my part, I think MIPS was very good to Cherry in the history, but I would really be happy if the MIPS code was gone from CHERI LLVM. All right, let's have lunch.